All right, hello, my name is Joel Ross, and this video aims to sort of answer the question, what is programming? And otherwise provide some context for sort of what we're going to be learning, what we're going to be talking about in this class. While this doesn't necessarily cover the how to go do programming yet, this is going to sort of try to, again, provide some sort of a framework and sort of how we want to think about what programming is actually doing. All right, here we go. So, in a nutshell, programming is about telling computers what to do. So when you're programming a computer, you are giving it instructions about what that computer should be doing. Basically, programming is like writing down a list of instructions, right? You're providing a sort of think of like a script or sort of a thing for a sort of a set of instructions for the computer to follow in order to go achieve some particular kind of task. And that's really all programming is. There's then levels of complexity about how complex you want the types of things you want the computer to do are, and how complex the movements and the blocking of that script might be. But in the end, we're just telling the computer sort of what we want to be able to do. Now, you don't need to program to use a computer, right? You can use a computer through using its own interface, using its own kinds of system. But generally, the reason that we're going to be writing using programming in most programming kinds of contexts, particularly in sort of high school kinds of contexts, is that we're really interested in trying to figure out how we're going to use a computer to help us work with some kind of data, with some kind of number, some kinds of records, some kinds of databases, some kinds of, I won't say information, but some kinds of sort of raw sets of data, which we can then convert into some kind of information, right? We want to be able to then produce some kind of this should be interpreted data here. It's getting blocked by my little screen here. Interpreted data. See how I structure my slides. This is really then coming from, again, sort of like our goal with the information school, right? We're making information work. We're going to say, well, how can we take that data and actually do something with it? How can we make that information actually do some kinds of tasks? And the idea is we're going to then use computers to help do that work for us. So we're going to get the computer to help us tell the computer how we can then convert that data into information. These are the kinds of examples you'll see of programming in Python getting used in sort of library science kinds of disciplines. So here's sort of just like the search example for what happens when you search for Python in the Code for Lib journal. And you can see things like we're using Python to take we're going to use programming to take the data that is a bunch of subject headings for journals and then be able to interpret that in some ways, right? We're going to get the computer to help us out with that. We're going to be able to take sort of place names and sort of where records might have been sort of originated from, and we're going to again use write some script, write some programming to tell the computer how to then combine all that information together. So the idea here is that we're really much we're using programming in order to be able to again take some existing sets of data, some information that exists out in the world, and then really sort of process it and understand it and organize it together automatically rather than trying to do that by hand. So it's kind of a sort of a kind of more specific example. This is not a library science specific example. So like here's an example of some data we might want to convert into information. This is one of I won't say my favorite data sets, but this is a data set of emergency room visits that involved coming from injury that involved a consumer product. So if someone hurts themselves with a vacuum cleaner, that goes into this data set. This is from 2014. I'm sure it's been updated since then, but like that's sort of a set of data we're looking for. So if we had some data like that, we might want to then start asking questions like, I don't know, what's the product's the most dangerous, right? Which vacuum cleaner is most likely to cause people to end up in the hospital? So again, that's a way of saying we have some data, right? We've got some bunch of raw numbers, and there's a lot of these raw numbers, right? You'll see there's like 266,000 rows here. There's a lot of injuries that come from consumer products. I don't know how many from vacuums, but there's a lot of them from computer products in general. And if we want to then get some information now, that's something we can be able to act on, right? We want to respond to, we might try to say, well, can we figure out then which product is the most dangerous? Something we can do. So this is a searching problem, right? We're going to sort of search through all the products and try to figure out which one is causing the most accidents. There's some variation, and we'll talk about some ways of putting that together. Cool. So we can get a computer to do this. But if we put the computer aside for a second, if we think about how we're trying to solve this ourselves and how we'd want to do this by hand, we could do that, right? If you imagine that we took this set of data, all these reports, and we like printed them out, we had to create a giant pile of paper that had just a listing of every emergency room visit involving, a vacuum cleaner. We could figure out which is the most dangerous by hand with a pen and a piece of paper. For example, we can go through by counting, right? We could go through and we could say, let's make a list of all the different products, all the different vacuum cleaners here, and let's go down the list one by one, and every time we see an injury with a particular vacuum cleaner, we just put a tally mark next to that vacuum cleaner, and we just count them all up, right? We tally everything, the kind of thing that you've probably done in the past. And then once we're all done, we then go through all of our tally marks and say, okay, which product had the most tallies, and whichever one has the most tallies is the most dangerous. Yeah, my mouse disappeared. All right. So this example of like tallying these things up is an example of what's called an algorithm. And so algorithm makes me like a scary sounding word, but really an algorithm is just a step-by-step set of instructions for solving a problem. So the instructions of go through every product, put a tally mark next to that product, and then, if it appears in our page, and then count up the tallies, figure out which has the, and then go through and search through which one has the most tallies. That's an algorithm, right? That's a set of instructions for solving a problem. And so that's what we're often going to be doing in computer programming, is that we're going to be trying to basically give the computer an algorithm, a set of instructions for it to follow to be able to make this work. So given that list, right, that algorithm, that set of instructions, that's something that's followable, right? We could give that to a person and say, hey, we could go find like a research assistant and say, hey, research assistant, please go count up all these products and figure out which is the most dangerous. Now we don't want to do that, right? Because that's a pain in the butt. So we don't want to do this by hand, because we don't want to actually like get a piece of paper and start like stacking and running through all those tally marks, because this is going to not work, right? This is going to be slow. It's going to be tedious. It's going to be slow. I mean, there's like 26,000 entries, right? It's going to be super tedious. It's going to be so bored. And it's going to be really error prone, right? In that the likelihood of you, for example, putting a tally in the wrong place or losing your spot is really, really high. So likely that things might fall apart. You'll also get these questions about, for example, how we want to scale our work, right? If we want to be able to say, apply this, like if this is just the set for US products, but we want to be able to consider this in an international context, right? How do we then do that without having to go do a whole bunch more tallying work? How will we reproduce our work? We go to the Acme Corporation, we say, hey, Acme, your vacuum cleaners are hurting many people. And they say, you're putting hundreds of thousands of people in the hospital every year. And Acme says, that sounds implausible. How's that working? We want to be able to sort of demonstrate that like there was an accounting error and sort of be able to show how we're doing that work. So we don't want to do any of this by hand. Instead, what we're going to do is we're going to basically find ourselves this like research assistant, this other person who's going to be able to go through and do all this like counting work and this tallying work without getting bored, without complaining, and without like making mistakes that deviate from the instructions, right? Without like getting lost on where they are. And that's what the computers are, right? Computers are going to be these systems that are basically just going to go through and follow an algorithm that we're able to describe. And these algorithms are generally going to be like counting things, right? Computers basically just do math. And so we're going to be defining, so programming is really going to be about figuring out what are these algorithms that we can follow, and then telling the computer to go follow that algorithm. That's really all that's involved in doing, I say it sort of flippantly, but that's sort of what's involved in doing programming. That's what programming is figuring out what are the steps you want a computer to do, what's the algorithm, and then telling the computer to go do that work. Okay. So as a fun fact, the very first computer program ever written was created by Ada Lovelace, who developed it for a machine called the analytical engine, which is sort of like a sort of early protocomputer that worked on the same mechanical principle as like a weaving loom. So she wrote an algorithm for how to compute what are called Bernoulli numbers, which are sort of like, you can think of like prime numbers. They're not prime numbers. It's a mathematical sequence of numbers like primes. And so she came up with, here's the algorithm, here's a language the computer would here's a way the computer would understand that, even though the computer didn't actually even exist at the time, right? So Charles Babbage had designed this hypothetical machine that may come to exist, and Ada Lovelace said, great, if that machine ever was actually built, here's that program that would make it do some work, which is cool. So yeah, the other really fun part of the story then is that Ada Lovelace was the daughter of the Romantic poet Lord Byron, and so she was raised by her mother, who hated her father so much that she made sure that her daughter learned and loved mathematics because she didn't want her daughter to become a poet. Because, poets, right? Anyway, so that's our goal, right? We're going to try to figure out how to tell the computer instructions about what it wants to be able to do. Great, cool, so that's where we're going. We need to tell the computer what to do. And if we do that, we'll be programming. The challenge then is that computers don't actually speak English. We can't just tell a computer, go through the number, all the records here and tally up the ones that we want. Computers won't understand that kind of language. So what really is involved in programming, sort of the hard part here, is not just what are the steps we want to follow, what is the algorithm, but also then being able to write those instructions in a language that the computer can understand. Right? We need to speak computer in order to tell the computer how to follow these kinds of steps. So the language that computers speak is called binary. So computers actually just speak zeros and ones. So binary is kind of like it's base 2, it's sort of mathematics. Right, and this roughly corresponds to whether like an electric circuit is like, whether electric voltage is going through a circuit or not. Very, very roughly, right? If there is electricity going through something, that's a 1. If there's not, it's a 0. And if you have a whole bunch of circuits, that produces your math. And that's what computers are doing, right? Computers are really just doing math. In the end, and that's part of why we're going to fall back to a lot of mathematics examples, because computers often are really just doing math at the most basics. And that's it. Everything about your computer that you've ever worked with is just, in the end, a bunch of addition and subtraction. And they're really not even subtraction, it's just addition, right? It's just the computer moving numbers around. That said, we don't want to learn to speak binary, right? We're not going to program by trying to write down zeros and ones. That's horrifying and terrible. What we're going to use instead is what's called a programming language. So a programming language is going to be a language that humans, the important parts, can read and write and, figure out how that works, but which can be interpreted by a computer, which a computer is able to take that language and translate it into a specific set of zeros and ones, which then correspond to the algorithms, to the steps we want that computer to be able to do. So again, computers are doing this interpreting step, right? This word interpreting is sort of a key point. We talk about the computer's interpreter, which is going to take the programming language, the code that we write, which is written in a code, effectively, and they're going to be able to take that and interpret it into steps that will then help the computer to actually go do some work, do some things. All right, so these are languages in their own right. They're not natural languages, they're called formal languages, but they have their own vocabulary, they have their own grammar, and they have their own syntax, just like foreign languages. Now, it's going to look a lot like English in some ways, right? A lot of the vocabulary are the same, are shared vocabulary with English words, but the syntax, the structure is very, very different. Moreover, computers are really, because we're trying to do this interpretation work, and computers aren't people, they don't understand nuance or inflection or context or any of those other wonderful features of language. It means that computers are very, very precise, right? We have to be able to give them instructions. We have to be able to speak this programming language in a way that the computer will be able to convert it back into the zeros and ones that it actually understands. The computer can do that interpretation. What this ends up meaning is that computers are incredibly literal minded, right? There's no context or nuance here. Computers will do exactly what you say and only exactly what you say. So it means that when we're trying to then figure out how to do programming, we have to be, and trying to learn this language, it's not just like learning a foreign language, but it's learning a foreign language with really, really, really precise rules. And if you don't follow those rules, you don't communicate correctly at all, right? You can't rely on your unlike with normal language, natural language, you can't rely on your listener to help interpret and communicate what you might be trying to say. With a computer, you just have to speak in such a way that the computer can definitely understand what you mean, and if it doesn't understand what you mean, it will let you know, and that what you tell the computer to do won't actually happen, and you'll have to then figure out why. So learning a programming language is a lot like learning a foreign language with a teacher who refuses to speak in your native tongue and then kind of yells at you whenever you make a mistake, which is part of the frustrating parts about doing programming. Okay, there are thousands of programming languages that exist in the world, and there's like new ones invented every year. I want to say not quite every day, but every year. They're slightly different. So the ones that we're going to be learning in this class is called Python, and there's some more details about Python in the readings and sort of in the other videos. So while there's tons of these languages in the world, they all have sort of some of the same basic ideas, right? It's the same way that like natural languages all have, or mostly have verbs and nouns and tenses. Even if exactly what verbs are and what nouns are and like how tenses are, what tenses exist, even if that's different across languages, they share the same overall structures. They kind of work in the same way, right? You put words together in more or less a limited set of fashions. The same thing happens with computer programming. Is like, while we might say we're going to have a whole bunch of vast different sets of vocabulary and different sets of punctuation, different sets of syntax, they often get put together in kind of the same general ideas, right? They'll still have what are generally verbs and nouns-ish kinds of equivalencies in programming. So we're going to be learning Python specifically, but a lot of the structuring and the way we're going to be learning Python is really going to be trying to lean on what are these sort of foundational ideas that show up in all programming languages, so that even if you need to go do some programming that's not in Python, right? You go do some programming in R, Julia, or whatever else you're working with. You can do that with, you'll be able to have some sort of some basics ideas that will let you be able to apply to other kinds of programs. Okay, so here's an example of Python as language. It's a math example. I again apologize for all the math examples, but this one's applying the quadratic formula. If you might remember that from school, which is always that math thing that people always thought was like complex and then hates, but that's what that is. So again, it's a way of doing this thing that's a math that people think is complex and hate, and it does it automatically by writing out some code to do that work. So you might squint at it and be like, okay, it kind of looks like math, but there's also some words in here. That's kind of what programming is going to end up looking like. As we look at more of the stuff, you'll get used to some of this syntax and some of being able to read this language, and it won't look like gibberish. The same way that when you look at any foreign language, as you start learning more vocabulary and understanding more of their syntax, it stops looking like gibberish. We will be able to understand how all this stuff works pretty soon, actually. This is actually a fairly basic example. Okay. The other thing that I want to then note about programming languages is that programming languages are all examples of providing what's called abstraction, which is really one of these key ideas in doing programming. So abstraction is this is like literally the main power of all computing programming, all computer science stuff is abstraction, which is we call generalization. It's basically the idea of working with higher level representations and higher level ideas rather than trying to deal with the specifics. So rather than trying to, the example I often use is that rather than when you go driving a car, when you push on the gas, the car goes, and that's the level of abstraction you think of, right? Push gas, car go. Like that's where you think of. You don't need to think of all the details like, well, when I push the gas, that actually increases the fuel injection into the combustion engine, which then does this other kinds of thing, which then moves this axle over here, which then spins these wheels. Like there's a whole bunch of details that go on with cars. And I'm not a car guy, so that example might be totally off. But we don't have to think about that, right? We just think like gas, go. So that's what is going to happen with a lot of programming, is that we're often going to try to both do some kind of abstraction work. We're going to say like, okay, sometimes I need to not think about the details. I can just think about, well, if I write this code, the computer does the thing that I want. Sometimes we'll need to think through, okay, I'm going to try to create my own abstractions. I'm going to write my own sort of generalization steps so that when I can then say, I can write the details about what happens when you push the gas down to make the wheel spin. And then I can later just say, push the gas down because I already explained what that means somewhere else, right? I've already sort of created my own definitions, which I can then work with in the future. So this is this abstraction process we're going to be doing a lot of as we're programming. It's going to be the idea that's going to sort of keep popping up kind of in the background again and again as we keep doing this kind of generalization kind of work. So again, another keyword to sort of keep an eye out for as you're developing programming. Okay, cool. But yeah, so that's really sort of the overall objective of where we're doing the course, right? Our goal in this class is to learn to give instructions to computers in a way they understand it, so they can go do the boring stuff like tally up dangerous vacuum cleaners, or do the boring stuff like look at every single web page from this, from this library catalog and be able to calculate how these holdings are organized. Is we want to take, they go look at everything on this web system, go look at all these examples and group them together, right? We want to have the computer do all that boring stuff. So we're going to basically learn how to tell the computer to go do all the boring stuff. And that's what this class is about. Okay, and again, the challenge then here is that in programming, there's really these two things that we're going to need to be dealing with simultaneously. We're going to be dealing with the syntax, right? Which is, how do I speak computer? How do I speak Python? How do I tell the computer to do this particular thing? So the question of, how do I tell the computer what to do at all, right? How do I get to communicate it in a language that it understands? This is a question of syntax, right? It's grammar. How do I speak the language correctly? And then the second question is often going to be one of algorithm, right? Which is not only how do I tell the computer what to do, but what should I be telling the computer to do in the first place that actually solves my problem? And these two things are related, but very different, right? We can come up with algorithms that are not language dependent, right? We can say, here is the series of steps I would go through in order to count up this, in order to tally the system and figure out what's the most dangerous vacuum cleaner. That's an algorithm I can do that's not dependent on a computer. Syntax would let me say, well, here's how I can tell the computer how to tally things and how to do this work, but I can define a bunch of syntax and tell the computer to do stuff without having any meaning or purpose or goal behind that. So in programming, in this class, we're going to be trying to lean mostly on the syntax, right? About the question of how do I tell the computer what to do, with the idea that I'll mostly be providing algorithms to you, or at least telling you here's an algorithm you can use, or we're using really, really basic algorithms like how do we get the average of two numbers, right? Well, you take the two numbers, add them, and divide by two. Or take a bunch of numbers, right? Add them together and divide by how many there are, right? That's how we take an average, which again, I'm hoping is a level of math that you're comfortable with. That level of math, right? Taking averages. Yeah. But so the idea is we're going to be working with really simple algorithms, or providing you algorithms, or trying to then walk you through the more complex algorithms. But a lot of times what you'll need to then figure out is that when you're working through programming, is the problem we're dealing with a syntax problem? Is it that I can't tell the computer what to tell the computer what to do at all? Or is it an algorithm problem? I can't figure out how to tell it what to do. I can't figure out what to tell it to be doing at all. Yeah. So often you'll need to sort of address these pieces separately, right? So maybe if you're struggling with, well, what do I even tell the computer to be working on at all? We can try writing that down, not in terms of syntax, but just being like, okay, what are the steps I want to go through? And then once I have those steps figured out, that algorithm at a level of abstraction that will like meets what the computer does. I can't just say, hey, computer, find the most dangerous product, because the computer doesn't understand that. I need to go more concrete. I cannot be that general. But once we've then come up with that sort of algorithm, then we can then focus on what's the syntax, right? How do I tell it to do that? Or alternatively, we might be saying, okay, my syntax is okay. I figure out, or maybe the idea is I have my algorithm, I need to struggle with my syntax. Or maybe the idea is my syntax is fine, I understand how to tell the computer to do things, but I can't figure out what to tell the computer to do. We might need to address one problem at a time. So keep in mind that there's sort of these two separate tasks you're sort of be dealing with when doing computer programming, which is both figuring out and sort of understanding algorithms, basic algorithms, right? Like counting algorithms. And also then syntax about how do I speak computer? How do I speak Python? Whew. All right. And so the one last piece is that for anyone who hasn't done this kind of thing before, programming is incredibly frustrating. It is probably one of the most frustrating tasks, most frustrating skills you could possibly learn. Programming involves a ton of failure. Nobody writes perfect code that just works and gets the algorithm correct and is syntactically valid. No one speaks the language perfectly the first time around. Even if you feel like you're fluent and you speak the language a lot, you still screw up, right? You still don't say the right thing. You still say it in the wrong way, and something fails. It doesn't work. Programming involves a lot of frustration. It's constantly failing. It's trying something that doesn't work, trying something that doesn't work, trying something that doesn't work, trying something that doesn't work. And that's can get really, really frustrating, get really, really hard. Basically, programming is literally, it's like teaching it's like teaching math in a foreign language to a petulant 6-year-old who then yells at you whenever you do something slightly wrong. So that's okay, right? That's normal, is that feeling of frustration, that feeling of, oh my God, it's failing over and over again, it's never working, it's never right. That's normal. That's part of how programming works. That's the skill, the task of doing programming. That's a normal feeling. That's sort of just what we live with all the time. So the metaphor that I like to use is that programming is a lot like doing a jigsaw puzzle, right? Putting puzzles together. And hopefully everyone has done this and hopefully kind of enjoys doing this. So this is what programming is like, right? If you're doing a jigsaw puzzle and you pick up a puzzle piece and you try to put the piece into the puzzle, and it doesn't fit, you're like, oh, it didn't fit. So you try to rotate a little bit and try it again, it still doesn't fit. And you say, oh, that was the wrong piece. That's a failure, right? You picked up the piece and you tried putting it in and it was wrong. It failed, it didn't work. But you don't feel like I've screwed something up or I've done something wrong or there's something wrong with me because you couldn't put the puzzle piece in the first time around. You just think, oh, that's fine. It's just a different puzzle piece. I gotta just try again. And that's what programming is like, right? Programming is like trying a whole bunch of different puzzle pieces. Sometimes they'll work and sometimes they don't. And often they don't work the first time around. You have to search through a number of puzzle pieces until you find the right one that actually is gonna fit. And then that one piece goes in and you're like, great, that piece is in, that's awesome, and now I start over with the next piece, and I also have to then pick it up, try it again, and have it, again, not go into the right spot over and over and over again until eventually my puzzle can come together. That's what programming is like. So just like when your puzzle piece doesn't go in together, it's not that there's anything wrong with you or that you've done something wrong. With programming, if it doesn't work, if something is having problems, if you fail to speak the language correctly, that's not a problem with you. That's just how programming is done, right? No one speaks these languages fluently or naturally. They're not natural languages. So there's always, you get some mistake somewhere, right? You picked up the wrong puzzle piece. You picked up, and the syntax was wrong. You put it in the wrong direction. Your algorithm was wrong, right? You tried finding a piece that was from a different section. There's lots of ways these things can go wrong. And that's okay. That's normal. So if it doesn't work the first time, don't feel like you screwed something up. Just think, okay, that was the wrong puzzle piece. I got to pick up a different puzzle piece and try it again. And what we'll do is that as we learn to do more programming, you'll get better at doing these puzzles. By which I mean that you'll get better at selecting the right piece and putting a piece into the right spot without having to test it each individual angle and sort of just like do it through trial and error. You know, you'll get used to being like, oh, I can realize that there are edge pieces. And then they can start being able to use that information to figure out how you're going to make sure you're fitting the right things in. You might be able to say, I can start being better at identifying that the colors match. I can start being able to find other kinds of tricks and tips that make it so I'm better able to put these puzzles together. So you will get better at doing this kind of work with practice. And as you sort of learn and sort of begin identifying some of the patterns in this language. But nevertheless, even as you're going to get great at puzzles, you're still going to, screw it up as you go. And that's normal. That's okay. So the line here is that if you're getting frustrated about it, if you're feeling like, oh, I'm screwing this up, I'm no good at it, the answer is that that's not the situation. You're not screwing up. You're not doing anything bad. There's nothing wrong with you. It's not even that you're not good at this. It's just that you haven't figured, you're still learning, and that it's a puzzle, and it just takes time to get the puzzles done. And that's normal. So that's really okay. So this is going to be programming is a frustrating experience. This is an exercise in frustration, and it has been, and I've been doing this for decades, and I still feel that frustration all the time in programming. But don't panic. Don't worry about that. We are here to help. We're here to help you get through that. A lot of times, really what you just need to do with programming is just being able to take a deep breath, realize, okay, it didn't work that time, but that's okay. It's not that I did anything wrong. I can now look and see, that puzzle piece, right? Its little connector was too big. I better look for a smaller one, right? You use the fact that when something doesn't work, you use that as information to figure out how you can then find a better solution and figure out how to actually make something work as you go. So this will be frustrating, it will be challenging, but if that happens, the key here is to make sure that you don't wallow in that and don't get stuck in that on your own, but to come ask for help. The general heuristic I like to give students is that if you get stuck on like a problem, if you're like sitting there trying to program and trying to get something to work for like 30 minutes and making no progress, like you have no idea what's going on and you're feeling like you're not getting anywhere, that's when you ask for help, right? Don't wait 3 days or hours or weeks to be like, okay, I didn't get this. If you get there for a couple of minutes, like 30, half an hour is usually a good run, that's when you go ahead and ask for help. If you get lost, you're confused, you're not sure, are you dealing with the syntax or the algorithm problem, you're just sort of getting stuck with that overall, ask for help. If you just get frustrated and you're just like, I need to just like vent about how horrifying this is and how terrible this puzzle is and how much I hate this, I want to throw all the pieces on the floor, that's okay. That's normal. Ask for help. Come talk to us, right? Let us work with you to help you get where you need to go. So again, that's how programming is going to work. It's going to be challenging, it can be frustrating, but it can also be really successful, right? Eventually you go through all this failure, and in the end, your puzzle comes together, and it works, right? Your program prints out the word banana, and you're just like, woohoo, bananas! And then, everything's great. And yes, that's actually what programming is like. So it's worth it in the end, it's just a lot of frustration to get there, and it's really, really useful skill once you've got it. So stick with it, spend a lot of time asking for help. Don't panic if it feels like it's challenging, if you're struggling at the beginning or struggling in the middle or struggling at the end. Don't worry about that. That's normal. That's part of how programming works, right? That's the skill. You fall off the bike and you get on it again. That's how that works. And in the end, you'll be able to tell this damn machine how to actually make it do what you want to do. Great. So that's the basic idea behind programming. The next set of videos will, of course, then talk about how we actually start doing programming in Python in a language we can actually understand. And as always, if there's questions or if there's frustrations, let me know, and we'll be able to help you work through that.